In this video, I'll explain how to do the first data analysis assignment of my quantitative analysis course or quantitative research methods course using Stata. And Stata is one of the two statistical software that I use for my empirical work. I also use R, but Stata is a bit more user-friendly compared to R. So if I have to do an analysis, then Stata is typically my default choice. The assignment here on the course website, you can access it using guest access. So if you know the course code, you can just type it into my courses alto.fi search and view the assignment. It is to use the Prestige dataset. So this dataset is data on occupations and their incomes and education levels from the Canadian census from the 1970s. It's from John Fox's Applied Regression Analysis book. And this is the command for loading this data. So I'm going to load the data first, just to get some data into Stata, and then I'll show what the Stata user interface is about. So the overall plan is to first walk you through what Stata looks like, and then go through and show how you actually do the analysis. We'll first explore the data a bit, then we run some regressions, we do some diagnostics, and then we export the results, and finally produce a report using exported results. So I'm going to paste the command here, and it loads the data. If you find it problematic to load the data, for example, if you get an error, then something that has happened over the past is that the UCLA website where we load the data, they change the location of the data. So if they change the structure, then this link might be broken. If you are looking at this or watching the screencast later and it doesn't work for you, please check the correct link on the course website. All right, now, what is Stata about? And this is Stata with factory settings. So this is just three Stata. And we can see here that we have three panels. So panel 1 here, main panel, and panel 3 here. Your Stata might look different. So if you're using Stata on a laptop screen, then it might be showing on sidebar layout, which means that you only get this one sidebar instead of two sidebars. But most people who analyze their data are probably using the widescreen. So I'm going to use the widescreen because that's what you would use on a big monitor. But if you are on a laptop, then you can use the one panel layout instead of the widescreen. So what do we have here? This is the results window. So you can see the name of the window here. And everything that we do, all the analysis results, everything that Stata produces comes here. So regression tables, correlations, error messages, messages that data were modified comes here. And then we have the command window here. The command window is something that the professional researcher uses a lot. So we can just type something here, type Stata commands, and then Stata will execute them for us. So for example, we can ask Stata to display 1 + 1. So it's going to be 2. So you can use Stata as a calculator. Why professional researchers use the command is that the window to type is that it's a lot faster to type commands like regression analysis that type the variables instead of using Stata through the other way, which is the menu. So we can use our statistics menu here, linear model related, linear regression, and then we have this dialog. We click through all the tabs that we want, and then we run the analysis. So just typing the name of the command is often a lot faster if you know the names of the commands. But if you don't know the names of the commands, if you're just getting started, then using the menus is probably a better option for you. I'll be using the menus throughout this screencast to show how Stata works. Then a third way to use Stata is to do something called a do file. So we can open a do file editor here, and the do file editor would contain a sequence of commands, and then Stata will execute those commands sequentially. Getting to talking about commands brings us to something that differentiates statistical software from Excel. So if you analyze data with Excel, you are usually looking at something like this. So you have the data, shown on a sheet with rows and columns. We can see that in Stata as well. And then you would do your analysis here. You could, for example, click on a cell and then just type something here and calculate an average, for example. So your analysis and your data live in the same file in an Excel. Statistical software doesn't work that way. So in statistical software, the data are what they are. They are in a file, and the data file should never be edited. For example, we can't even edit this here, so it's all read-only. How we manipulate the data, how we analyze the data, is that we execute a series of commands. For example, we might first execute a command for calculating means of the variables. We might look at the means. Then we might notify that there's a data entry error. We might execute a command to fix that error. Then we could run a command for regression analysis, and then a command for exporting the regression results to a Word document. So instead of thinking about the data and analysis as cells, you have an analysis file that contains all the commands that produce the analysis result that you want. And then you have the data file that is the starting point. All right. Now let's take a look at, once we know how to use data, so there's the command, there is the statistics, and then there is the do file editor where we can type many different commands. On the left, we have history. So the history tab shows us all the commands that we have run this far. So if you want to know how to produce the results that you just got, the history shows you that these were the commands that you run. We can also see how the history reacts when we do errors. So let's type display and let's do a typo that produces an error. And we can see red here shows that this was an error. So whenever we want to, if we ever want to rerun this analysis again, we would know that we should not run this line in red, which is an error. Then on the right hand side, we have the variables panel, and then there's a project browser if you are working in a bigger project manager. I don't use project manager, but some people like it. We have variables, so the variables are here. So if we want to calculate the mean of the variable, we would do, for example, sum, which is short for summarize, and then we can type the name of the variable, occupation title. It gives us the mean, but that's a bad example because that's a string variable. So we can calculate the mean of the variable income, so sum income, and so we refer to the variables by name. And then this label is a more descriptive name. It tells us what that variable is about. And if you do figures or if you export tables, they always use the label. So if you are someone who reads an analysis result from a journal article, for example, you want to see the variables explained like a type of occupation instead of OCC_type, which doesn't really tell anyone who is not working with this data what that is about. So the variable name is something that we use to refer to the variable, and then the label is more like a descriptive name of the variable. And we have properties of the variables. So when we pick a variable here, we can see that this is a string variable. So the string variable means that it is text, and text variables can be analyzed statistically. Like I tried to create a summary, calculate mean, standard deviation, minimum, maximum for the variable. You can't do that. Mean doesn't exist for text. Then we have education here, so it's float. Float means that it's decimal number, and then we have occupation type here, byte. Byte means that it's a small whole number, so small integer, and it also has a label here. So occupation type is a labeled numerical variable. Then up here we have a log file viewer. I don't normally use the log files because when I run an analysis, I always store the commands into a do file, and if I want to recreate what I see here, I'll just rerun the do file. But if you want to, for some reason, save your log like you would do in this assignment at the end, then you can do it from the user interface here. So there's this begin, append, view, various logging options. Viewer is the help viewer. You can also type here for search. That will give you help. And graph, if we have graphics open, we can look at the graphics windows here. The do file editor opens the do file editor where we can specify a sequence of commands. I'll show that at the end of the video. And then we have data editor and data browser. You should pretty much never use the data editor unless you are generating like a small example data for yourself, or typing in a data set that you have gotten in a non-electronic format, which you might get, for example, if you have paper-based surveys, then you might type them in. Data should never be edited directly, because if we change something here, so for example, if we change the income of the government administrators to be 1, then it doesn't really document what was done. So it just tests that income was replaced to be 1 in observation number 1. That's not very descriptive. So it doesn't tell us like why did we choose that variable and why did we pick value num1. It's much better to do any changes using commands. So I'm just gonna reload the data. Generally, you shouldn't use the data editor. If you want to eyeball the data, then you can use the data browser. So the data browser is the same as data editor, except that this is read-only. So we can't edit anything. We try. It doesn't allow us to edit. The data browser shows us that we have 3 different kinds of variables. We have red, we have black, and we have blue. So the red indicates that it is a text variable. So we can see that this is a value, it's government administrators, and it's text. Black is normal numerical variable. And then this blue is labeled categorical variable. So it's a numerical variable with labels. So it's this professional, for example, has a value of 3, but it's going to be shown with the label in the output. The reason for that is that in categorical variables, the actual numbers, so we have numbers from 1 to 4, corresponding professional, blue collar, white collar, and unknown occupation types. It doesn't really matter, so we can't say that if unknown is 1 and blue collar is 4, then blue collar is 4 times unknown. It doesn't make any sense. So these are just codes, and the numbers don't make any make a difference. We could recode them with different numbers, and the analysis for the conclusions, it wouldn't matter. So for that reason, we are always printing these categorical variables with the label instead of the numerical value, because the value again is arbitrary. All right. Then we have a couple of buttons. We have the More button here. And the More button, what it does, I'm going to switch to the menus in a minute, but I'm going to show a few features. One annoying feature of Stata is that when you start it the first time with the default settings, it only prints you 1 screen's worth of output, and then it says More is coming, and it stops. And we can click there, or we can click on the More button. And then you can view the rest of the output. I don't like that feature, and I don't know any professional researcher who would use that feature. Maybe someone does. And it's a lot easier to just scroll back if I want to see the output little by little, instead of typing more. The only use where you might have for more is that your output is so large that it doesn't fit into the Stata results window. Then you might find some usefulness from the More option. But you can just increase how many lines of results this results window shows, and it can be pretty large. So it's if you change the settings, then that eliminates the need for more. So whenever I start analyzing anything with Stata, what I do is change a few settings. And I recommend that you do this setting changes yourself as well. So we do set more of, permanently. And the permanently means that it's going to be stored in our preferences. And when we restart Stata, then we don't need to do set more of anymore. If we do without the permanently option, then the preference is stored only for this session, and the More option is going to be on again when we restart Stata. So we do that. Another feature that Stata has is variable abbreviations. So for example, if we type sum I, then it shows us the summary of income. So you can do these abbreviations. If we do, let's do describe O, then it says that O could mean two different things. So it's either occupation code or occupation type. So I turned this off. And the reason why I turned these abbreviations off is twofold. First of all, I think if you always type the full variable name, then it produces more readable Stata code for someone else to interpret. And it also avoids errors. So when I used to have this abbreviation feature on, then I might have inadvertently analyzed an incorrect variable because I had just type a few letters from the beginning of the variable. And when I have variable names that are very similar, it's very easy to analyze an incorrect variable. So we're going to turn that off as well. So the setting name is set var abbrev off, permanently. And now you can probably start to see a pattern that Stata commands is always a command. Then there is a main specification, and then there's an option. So the options are something that kind of like give additional information for Stata on what the Stata should be doing. All right, and now if we can do sum I, it tells that the variable I is not found because it doesn't do abbreviation anymore. So when I do something then with a new set of Stata or new install of Stata, I always set them all off and variable abbreviations off because I think it makes working with Stata a bit less error prone and more pleasant. All right, then another preference that you might want to change is changing the font size. So if I present in a class, then you just right click somewhere, preferences, and you can increase the font size. I tend to have 10 when I analyze data on my computer, but this is set to 15 for the screencast. And then the command window is set to 15, and I think that's good for the screencast. But if I analyze data myself, I would have 10 just to have more information shown on the screen. All right, now let's get to the analysis. And what we need to do first is to explore the data. And the data exploration typically starts by doing univariate statistics. So we have here the statistics menu and data menu. These contain various different expression commands, and I don't use this very often, so I might need to look for a command a bit. But describe data, we can do describe data in memory or in a file. All right, so that tells us something, and when you do a command from the menus, then you get this kind of dialog, and the dialog asks us what to do. So we want to describe data in memory. We leave it empty, so we want to have description of all the variables and not just a subset. And then various options. And typically the defaults, at least on a very basic level, are going to be useful for you. So you don't need to change any of these unless you specifically need to, in which case you would know the need. So we're going to describe, and that shows us a description of the data. So this description is pretty much the same thing that you would have here in the properties and in the labels here. So we can see we have one text variable, we have one decimal number, one whole number, decimal number, whole number, and then a small whole number with a value label, which tells us that this is a categorical variable. So whenever you start with a new data set, I typically print this describing just to show what these data are about. It's a lot faster for me to look at this than it's to look at the right panel. And in fact, when I use data, I typically don't have these panels open. So The command history, I can open it if I need it. I really do need it because I work with a do file, and the do file shows all the sequence of commands that I've done. And then I tend to remember my data, so I don't need to have a variable's name here. If we want to then do something for individual variables, like we can see the command is describe. If we want to describe an individual variable, we can either type the command, or we could redo the menus, and then we can type these, click on these variables here, and then press enter. So we can construct the command by typing the name of the command, and then clicking on the variables. If we want to redo the command, rerun the command again, we can use page up, and page up scrolls through or goes to the command history. So we can go page up and page down. We can kind of revisit what we've done in the past. So if you want to redo something, then you can just rerun the command. All right, another useful command in this data, in the data window or data menu, is inspect variables. So inspect variables are empty for all. We're going to inspect them. So this gives us something about like more descriptive statistics. And you can use wildcards here. So if we want to only do everything that starts with OCC, we could do OCC star. And that's actually useful because it shows how the descriptive or the inspection works for a string variable. See, there's like no observations here, no numeric observations, so everything is missing. It's just text, no numbers. And then we have the occupation code here, and then we have occupation type. So this is the categorical occupation code. It's just the code. It doesn't really tell us anything. Then we have a third way of describing the data. So something that professional researchers sometimes use is that if we have many people who work using the same data set, or the data set is something that you've collected for someone else to use, then you produce something called a code book. And the code book explains what the data are. It tells the variable names, it tells the labels, it tells the data types, like is it text or is it not numbers, is it whole numbers, is it decimal numbers, and then provides some descriptive statistics. So we can do our data, and then there is the code book, and I will have to look for it. It's in describe data. Yeah, describe data contents codebook. So this is another way of showing the data, and it's a bit more like verbose way. So it shows us statistics for string variables. It shows us examples, so we can see examples of what kind of things this variable has. So we can see that these are all caps. There are no spaces but underscores, and the longest one is 25 characters. Then we have this education. We can see that it has 96 unique values, mean standard deviation. Then this tells us about the distribution. So it's 10% is 7.52. So 10% are less than that. And then 90% are less than 14.17. So the number for education, the years of education is pretty small compared to current standards. Then there's the income, percentage bonus prestige, and occupation type. Now we can see this is useful information because this is a categorical variable. It shows us a bit different. It doesn't show us means because a mean of a categorical variable doesn't really tell us anything. Rather, it shows that we have 4 unknown occupations with unknown category, and this is the value for unknown is 1. The label is question mark. Then we have 45 blue collars that are coded as 2, 30 professional occupations, 23 white collar occupations. So, and there's no missing data. So everything, all 102 observations always have data for every variable. So that is the third way or fourth way of looking at the data. And or third way. Then the fourth way is through the statistics. So we have summaries and summary descriptive statistics, summary statistics. So this is kind of the thing that I use the most. And summary statistics, let's do additional statistics just to show what it looks like. It tells us basic descriptive statistics of each variable. So we can see that it added the option detail. If we run without that option, then we just get mean, standard deviations, minimums, and maximums. So I used both of these. And when you do univariate analysis, you want to understand what is the range of the variable, like what is the minimum and maximum, what is the mean. We can see here that there are, for income, the mean is 6,700, maximum is 25,000, and minimum is 600. So it tells us that the data are skewed because the distance from the minimum to the mean is 6,000, and the distance from the minimum, from the mean to the maximum is about close to 20,000. So the data are skewed so that there are very few occupations with very high incomes, but a lot more occupations with lower levels of incomes. Then standard deviation tells us about the variation of the data, and then this generally tells you about what is the unit, and it's useful for regression interpretation. Occupation type, mean and standard deviation, doesn't make any sense because it's a category, but we can see that there are four elements of four different distinct values, or we can guess that there are four distinct values in this category variable. All right, that is the basic description of the data. And then another thing that we would often want to do is to look at the distribution. So if you think about a distribution, you might think about a normal distribution, which looks like a bell curve. So it goes up, and then there's kind of peak, and then it goes, and then it flattens like that. So that shows where the observations are located. That's a useful display, and we can do that with Stata. So there are a couple of different ways of doing distributions. We can do statistics, and then there's distribution plots and tests, and these are various ways of characterizing or describing the distribution of a variable. Stem and leaf display is one of my favorite ones, and the reason is that it doesn't produce a graph, but it produces the graphic as text. So it doesn't open a new graphics window, but it just puts the results into the results window. And we pick one variable, so let's pick income. In practice, when you analyze your data, you would look at the distribution of every variable, and you might use stem and leaf plots or some other plots for that. So I'm just gonna do that, and it shows us the distribution. So if you look at this, it's kind of like a normal distribution flipped 90 degrees. So this shows us the first two numbers. So it's easier to the first two digits. So it's easiest to look at this instead of the small ones. So the largest value in the data is 25,000, and then these stars are filled in with whatever value is here. So the largest value is 25,879. So everything separated by comma means that it's a separate observations. So we have two observations in the 25,000 range, and they are 25,308, 25,879. Here we have two observations with 0 thousands, so 611 and 918. Those are the smallest observations. And you can see that the peak of the data is roughly around 5,000. So that the median might be somewhere here, 5,000 or 4,000, somewhere here. And so this is the stem and leaf plot. Then another useful way of looking at the data is to look at the kernel density plot. Yeah, we can find graphics, distributional graphs, and then there is kernel density estimation. So this is what I would often use, and we're gonna take a look at income and just leave everything as default, and that Stata graphics is a bit slow, but that shows us the distribution graphically. So the height of the line tells how many observations we have here. So we have 2 observations, 25,000 here, and most are here. So it kind of like looks like a normal distribution with a long tail. So it's skewed to the right. And we can also do the same graphic with options. So if we want to analyze if the variable is normally distributed, then we can go and look at these different options. So if in, this would be for selecting observations. We can choose based on a condition, or we can use a range of observations. We could use survey weights if we want to weight some data more than others. I never used it myself, but this is how we plot it. And then we have additional density plots. We add normal density plot, and that gives us a reference. So it gives us the normal distribution that best describes this data. And we can see that the data are not normal. They are more skewed than what the normal distribution would suggest. So if you want to analyze if something is normally distributed, this graphical way of using kernel density is the way to go. And so you can do that also. Typing k-density. Let's do education. Tab autocompletes the variable name, and then that shows us the kernel density of the education. When you analyze a data set, then you would use these 2 commands. You can pick either the kernel density plot or the stem and leaf plot, or you can do both, but they tell you the same information in different ways. You would do this for every numerical variable, except those that are categorical. So every continuous and every variable that has a numerical interpretation instead of a categorical interpretation, you would do this and then look at the distributions just to understand, like, do I have any extreme values and how the data look like. It's very important that you understand your data when you start analyzing. So that is the distribution and of the univariate analysis. Then what we need to do next is to look at multivariate analysis. And we start by looking at bivariate analysis. And because the point here is to do a regression analysis. Regression is a linear model, so we want to understand the linear dependencies in the data, and correlation matrix is the way to understand linear dependencies. So we want to do correlations next, moving to bivariate relationships. So we do statistics, and then you can guess where it is, but I'll just type the name of the correlations. So there's it is summary and descriptive statistics. So statistics, summary and descriptive statistics, and then statistics, summary, and descriptive statistics, and then correlations and covariances. We click all variables and we click OK. And now we have a warning from Stata that occupation title is ignored because string variable. In some older versions of Stata, if you try to correlate a text variable, it produces an error. And sometimes if you try to do, for example, a regression analysis with a string variable, it might produce you an error. But now Stata is smart and it drops the occupation type from the data. The occupation code is just a categorical code, and it doesn't really tell us anything. If you really want to understand what it is, it's like a census code. You can find the documentation of the Canadian census and see what the different codes actually, how they're defined, but it's not going to be a useful exercise for you, I guarantee. All right, so this is a way of looking at the data in a bivariate way. And if you think about a published paper, this would be the table 1, descriptive statistics and correlations. This would be the correlations part. Then we have correlations here, how we would interpret. We would check if the correlations make sense, like if there's a large correlation. This 0.57 is pretty large. So in social sciences, correlation of 0.3 is something that we would consider meaningful, definitely. 0.5, 0.6, definitely very large correlation. So there is a large correlation between education and income, and even larger between education and prestige. And then there is a large between prestige and income. Makes a lot of sense. If you have prestigious occupation, it's probably earning you more money. And then we have share of women. Women are discriminated against, so the income here is negatively correlated with share of women, and that's also understandable in 1970s. So that is the correlation. You would go through all the correlations and look at what are the large ones. Do they make sense? Are there some correlations that are small, like non-existent? Do they make sense? For example, we might take a look at education, and it doesn't seem to be correlated with share of women. That kind of resonates with our everyday understanding that both men and women tend to get education at about the same rate. So there is a small positive correlation, but that's very small. And the data are pretty small, 102 observations only. So this is one way to understand the bivariate relationships. Another way is to look at scatter plot matrix. So we do scatter, and then it's in graphics, and two-way scatter plot matrix. Yeah, graphics, scatter plot matrix. So I'm not going to talk about all these graphics. I'll just show the ones that are needed for this assignment. And we start with all the variables. Okay. And okay, we have to specify them. We click education, we click income, we click percentage woman, we click prestige, and occupation code is just the census code. It doesn't tell us anything. And then occupation type, that's categorical. It doesn't really tell us much, but let's still include it just to show what it looks like. And we click OK. And that shows us a graphical way of graphical representation of the correlation matrix. Let's make it a bit bigger. Now we can see that this is always the x-axis on the top, and then on the right or left-hand side is the income. So we can see that education is the x-axis here, income is the y-axis here, and the relationship seems to be increasing. So we can take a look at the shape of the relationship. Correlation just tells that there is a relationship. So this correlation but 0.5, income and education are 0.56. And this plot shows us what is the shape of the relationship. So this is not a linear relationship. So the income doesn't increase linearly with education, but rather it looks more like an exponential. So first there is very little increase in income, and then at about 10 years or something like that, it starts to go up quite rapidly. And that also makes a lot of sense, because if you think about how education works, is that for the basic education, which is now 9 years mandatory in Finland, and then you have either high school or occupational vocational school, then the first 9 years basically give you just the understanding of how to be a citizen, and then but it doesn't give you any professional qualifications. So only after the basic education you start to get some professional qualifications, and if you really want to get to a high-paying occupation, then typically it requires a university degree. So you get a lot more additional income from a university degree than you would get for a high school degree. So that's why it's non-linear. And then we have one outlier here. So this, I know the data. So this is general managers. And we can print the observation names here, but it doesn't really make sense for this plot because there is so much going on. We can see that education here and share of women, it doesn't correlate. There's like no clear pattern here. There is a clear linear relationship between prestige of an occupation and income. we can see a bit of, we would call it heteroskedasticity. So these are more spread out over here than they are over here. So these are some of the things that you can take a look at in this figure. Then we can see from the occupation type. So the occupation types are here 1, that's the unknown, 2, 3, and 4. We can see that the category number 3 is clearly distinct from the others. This is not an ideal plot for inspecting the differences between the categorical variables, but you can do so. So you would be looking at this plot and looking for patterns in the data. And these are just the mirror images of each other. So this is that's the general managers, that's general managers, and these are the low occupation, low education occupations. These are the low income, low education occupations. So this is just depending on which one you want to think of as the dependent variable. If we want to think of the income as the dependent variable, then like we do in this assignment, then we will be looking at this row. And then the y-axis is always the income, and then whatever is the other variable, like occupation, prestige, share of women, and education is the x-axis. So this is the second bivariate descriptive statistics plot that I want about a bivariate descriptive analysis tool that I like to use. The next thing after data exploration is to do the regression analysis. So the task was to explain the income variable with the other variables, and we're going to start by running one regression model. The overall workflow here is to go and run the first regression model, then do diagnostics for that model, fix the biggest problem, then run the second model, do diagnostics for that, fix the biggest problem, and so on. So what the problems are, I'll get to that. But the point is that you do a few different models where your model evolves, and then you explain your thinking in that and your interpretation of the results in the assignment. So we do regression by taking statistics, linear model related linear regression analysis. And there's quite a lot of, there's a few tabs here. I'll explain a bit what these do in a moment. But first we need to pick the dependent variable for regression analysis, and we'll pick income. And then we pick the independent variables. We'll have education, we have percentage woman, we have prestige, and then occupation code is something, it's like a census code, it doesn't matter. And occupation type is a categorical variable. We are not going to use the categorical variable in this assignment. If you want to use it, then you need to put I period in front of it to tell the Stata that it's a categorical variable that needs to be dummy coded. But I'll take it out for now. Then there is additional features about the model. This is typically you don't need any of this. Then the other tabs here is by, if, and in. By means that you're repeating the analysis by subgroups. If you want to, for example, analyze the regression for each occupation group, you can do so. Then if allows you to constrain which observations you apply for the regression to. So for example, you can apply regression only to those observations with at least 1,000 income. An observation range is useful if you want to run like quick analysis, but your data is very large. So you can limit the number of observations that you use. Weights, this is for survey weights. So if you have a survey design that is stratified, which means that individuals don't have equal chances of being included, but for example, some smaller cities are overweighted compared to, for example, Helsinki, if you do a survey of Finnish population, just that we have enough informants from those cities, then we would use these weights to accommodate that kind of sampling scheme. This is an important one, standard errors. You can pick various different kinds of standard errors. Robust and cluster robust are something that you would use. Robust is for dealing with heteroskedasticity, and cluster robust is for dealing with non-independence of observation. So these are very commonly used. And then reporting, there's all kinds of additional reporting options that you can use. You can pick which confidence interval you choose. Standardized coefficient, you pretty much never use this. And then in some models, exponenting the coefficients makes sense, but it doesn't really make sense in regression analysis. And then you can choose what to report. Then there's some additional options. So there's lots of options in each of these commands, but typically just filling the first tab is sufficient for most purposes. Then submit runs it right away. So if we want to run multiple models, we can submit. And then if we want to run another model, for example, take one of those variables out, we submit again. So submit runs the analysis without closing the tab. And OK runs the analysis and closes the window, like so. All right, now we have regression results here, and I'll cover the interpretation of these results more on the course, but we can see here that 1 unit increase of education leads to approximately $177 increase in annual salary, but it's not statistically significant, so here's the p-value. This is the confidence interval, and this is the t-statistic that is used to calculate this p-value. And you might wonder why education doesn't pay off, and maybe it's a mediation effect, so that education unlocks access to more prestigious occupations, and then prestige is actually what makes the difference. So that you would interpret this to mean that if you get more education, but you don't go for more prestigious occupations, then education doesn't really pay off. And percentage woman has a very strong effect. So for each percentage point, this variable is coded from 0 to 100. The amount of income decreases by -50. So if we have an occupation with 0% women and an occupation with 100% women, the difference is 5,000 Canadian dollars. That's a very substantial difference if you consider that the average income is like 6,000 something. So these are statistically significant, and this is not. Then we have other statistics here. You should take a look at the R-square. And the R-square tells how much the model explains the data. In management, 20%, 30% is very high number. But because this is sociology and the weight formation depends very straightforwardly on the prestige and occupation, this is a very large R-square. This p-value is the p-value of the f-test. So the f-test tests the null hypothesis that the R-square is 0, and then we have adjusted R-square, which is a bit better for interpretation than the actual R-square if your sample size is small. So R-square is always biased positively, and adjusted R-square adjusts for that bias. It's not fully unbiased, but it tends to be less biased than the R-square. Okay, now that we have a regression analysis run, we can do post-estimation. And in the statistics menu, there's this post-estimation dialog. So post-estimation refers to, it means all the tasks that one could do after estimating a model. So when we click post-estimation, there are various different options. So it's a pretty small window here, or the font size is small and it can be increased. Manage estimation results. This is useful for tabulating the results. So but first we need to store estimates in memory. So whenever you run estimates, then those estimates will be in memory, and you can apply, for example, various diagnostics plots. But if we want to return to the estimates later, for example, if you want to tabulate two sets of estimates side by side, we need to save them. So Stata, by default, when you run a regression or any other estimation command, it stores the most recent estimates in memory. So unless we save the estimates, then if we can only tabulate the most recent ones. So whenever we run a regression analysis, when we run it the next time, always the latest results overwrite the current results, unless we save them. So we're going to store the estimates. So we're going to estimate store. We're going to call this M1, and OK. Once we know that these results are something that we will be using, then I recommend always storing the estimates. But if you just explore the data, then storing the estimates is not necessary. You can see list estimates stored in memory, and you can launch it and list all stored estimation results. It shows that we have one stored, there's income is dependent variable, 4 independent variables, 3 independent variables, and the intercept, and then it's a linear regression analysis. All right, let's go back and do post-estimations. So we need to understand, do diagnostics after estimation, always to understand whether the model explains the data well or not, and if there's something that we can do about the results. So let's go to post-estimation again, and then we have diagnostics and analytics plots. And there are a few important, interesting plots: residual versus fitted plot, added variable plot, and then I also use leverage versus residual squared plot to identify outliers. These others can be used as well, but this is the combination that I use: residual versus fitted, added variable plot, and then leverage versus residual. So let's do residual versus fitted plot. And it runs, it produces the plot in a different window. And this plot shows us that this is the value that the model predicts. So it's the prediction based on the regression equation, the fitted value, and this is the residual. It's the difference between the fitted value and the predicted value. Ideally, these would be a band so that they would all be on average at 0, irrespective of which part of the data we look at. And then they should be distributed approximately equally around the 0 line, which is the homoscedasticity assumption. And we can see at least a couple of problems here. First of all, we can see that this is not exactly linear. So if this was linear, then we would have all the observations at around the 0 line on average. But for small observations here, they tend to be above 0. And for large values of fitted value, they tend to be also above this 0 line. And that tells us that the effect might be curvilinear. So it might be that it's not linear, but it's rather kind of like curving up a bit, like the relationship in comparison to the regression line. Another thing that we can see is that the variance of the residuals is a lot greater here than it's on the left-hand side, and this is evidence of heteroscedasticity or non-constant variance of the error term. So these are the two things that we can take a look at from this plot. We can, of course, identify individual observations that are distinct, like that is the general manager's, and it's an outlier, but this is not the ideal plot for looking at that kind of things. If we want to save the plot, then we need to rename it, and we can call it RVF, for example, RVF, residual versus fitted, and then it's going to be saved. And if we don't save a plot or name a plot, then redoing the plot or doing the next plot will override the previous plot. So but I'm just going to close it because we don't need this plot. The second plot that I want to show is the added variable plot, and particularly all added variable plots in one graph. And the added variable plot is useful for identifying nonlinearity and heteroscedasticity of one independent variable at a time. So I'm going to take all variables, click OK, and it runs. It produces a matrix of plots. And what these plots tell us, they tell us what is the unique effect of education on income, what is the unique effect of prestige on income, what is the unique effect of prestige woman on income. And these would be useful for identifying if one of the independent variables specifically has a nonlinear relationship with the dependent variable, and also identifying heteroscedasticity. So these plots don't show a nonlinearity problem as well as the previous plot, but this is an additional set of diagnostics that you can do. Then we have the leverage versus residual squared plot. And this is useful for identifying outliers. So leverage is a measure of influence. So how much an observation influences the regression results. And then if an observation has a large residual and large influence, then it's an influential observation and potential outlier. So we can see that here's a potential outlier, this is a potential outlier, and this is a potential outlier. But outliers are not something that we dropped based on just statistics. We need to understand what these observations are and if they are clearly distinct. And to know what these observations are, I'm going to close the plot and then I'm going to launch it again. And then there are plot options and we can choose marker properties and add labels to markers. So we label and we have the occupation title here. We accept and we click OK. And that shows us that we have an outlier newsboys, which has large influence, small residual, physicians, bit of both, and then general manager with a large residual. All right, so these are the plots that you will use for diagnostics. Then there is another kind of plot that researchers sometimes report or inspect, but it's not very useful, which is inspecting the distribution of the residuals. Predictions and predictions and the standard errors, leverage statistics, distance statistics, etc. We're going to launch, and prediction means that it's something calculated based on the model. And we are going to calculate the linear predictions gives you the fitted values. We are going to calculate the residuals. And we're going to call it R1 or Res1 because it's from the first model. So residual from model 1. And if we want to inspect the distribution of the residual, we can do graphics, distributional graphs, and we can do, for example, normal quantile plot, which is useful for inspecting normality. So if the data are normally distributed, then they should be on this line. But because these are above the line, it tells us that there's a tail. Some observations, some residuals are larger than what normal distribution predicts. And then there's this observation here that is a lot smaller than what the normal distribution predicts. If you want to see it in another way, you can have smoothing and densities, kernel density estimation, pick residual. Then we have density plot, add normal plot, OK. And that shows us the red is the normal distribution that best fits this data. And then blue is the empirical distribution of the data. So we can see that the data are a lot more peaked. There are more observations around 0 and longer tails on both ends, though more on the negative end than what normal distribution would predict. So this shows that the residuals are not normally distributed. That's not a problem in regression analysis, even though a lot of researchers think that it's a problem. So what do? We had evidence of nonlinearity. We had potential outliers. Then we had heteroscedasticity. We need to fix the biggest problem first. And the biggest problem would be the nonlinearity. And we can model exponential relationships, which are very common in nonlinear models. Very common way of modeling nonlinearity by taking a log of the dependent variable. And that would make a lot of sense because then it converts the regression coefficients to relative quantities. So instead of thinking about increasing your income by a certain amount of Canadian dollars, you increase the income as a percentage relative to the current income. So we're going to do log transformation of the dependent variable and create a new variable and then run the regression again. So we're going to do data and then we're going to do create variables, create new variable, and the variable name is going to be ln income. So I'm going to call it ln. Let's have it underscore, because that is the convention that we use in this data. And then we can either create the expression or we can just type log income. So log is the natural logarithm. You can create here, and then there's all kinds of functions if you don't remember the functions. So we can have, for example, our mathematical functions here, and this is the list of functions. So we can find the log, natural logarithm, log, and then x, we type income there. So that would be a way of using the expression editor, but it's easy to just type log income. And then we're just gonna, okay. And now you can see that it doesn't have a label, and we could label the data, but yeah, we're not going to do it for this assignment. The next thing we do is we run a new regression analysis. There are a couple of different ways to do it. We can either just go here, go to linear motion related linear regression analysis, and then we can pick the ln income as the dependent variable, click OK. Another option would be to just go back to the regression, scrolling back the commands, and then just changing the name of the dependent variable by editing it. So both are pretty easy. So yeah, ln underscore. Now we can see that the effects are fairly different. So this is relative effect. It means that for every additional percentage point of women, the income decreases by about -1%. So it's a relative effect compared to, it's no longer absolute effect. And then your task in the assignment would continue from here with the diagnostics. I will not do the diagnostics. I'll leave some for you to do. So you need to go through the diagnostics, interpret the results, and then choose which observations are potential outliers. I will now show how you drop a potential outlier from the data. So let's assume that, we go to the data editor, data browser, and we can look at observations with large residuals. So we're going to sort the data. Data, sort. And then we're going to sort by residual. So let's assume that minister is an outlier because it has a large residual, and the substantive reason for dropping ministers would be that minister, in this case priest, is something that you don't do for money, and it might also be a part-time occupation if you only work for weekends. So how church works in the Americas is quite different from how it works in, for example, Finland, where I'm from. So we might say that this is not a full-time profession, so we'll drop it. And now we sorted the data, so we could just say drop in one, but it's much better to drop based on the occupation title. So we can copy that value from there, and then we go to data. We can do create or change data and drop or keep observations. So we drop, and then the expression, we can use the expression builder by using the create here, but it's just easier to type. So occ title equals, so equals is two equal signs. One equal sign is assignment, two equal signs is comparison. And then because it is a string, it must be in double quotes. And then I'm going to drop it, and then I can rerun the regression analysis and see what the results are. Like so. And then I will store the estimates. I can either go to the menus, or I can see here that the command for storing the estimates is estimate store. So we can just type estimates store M2. And now we can go and view here all the estimates. We can either go and see the post estimation menu here. Post estimation, manage estimation results, list estimates stored in memory, and all estimates, or I can just do estimates there. Now, I dropped one observation and I transformed the dependent variable to be log. And the reason for doing this in one step is just to show these things that you need to do in the assignment. But in the assignment, you need to do the sequences. So if you decide that nonlinearity is the biggest problem, then you need to run the model again with the log transfer dependent variable, do the diagnostics, and then determine if any of the observations are outliers. For example, when you log transform the dependent variable, then which observations are outliers differ. So it's not a good idea to drop based on the original model, but you drop from the subsequent models. But just not to give you the full answer to the assignment I did in one go. Then we have a few things that we can do. We might want to tabulate these models. So there are a couple of different ways. Post estimation gives you then table of estimation results. So this is a quick and dirty table, and I'm going to say M1, M2. So this gives us two models side by side, and if we want to add things there, we can do statistics, post estimation menus, post estimation, table of estimation results, other statistics to be displayed, and other statistics from E. How do you know what this from E stands for? Well, it stands for whatever are the estimation results, and we can do help regress. So that's the help for regression analysis, and you can go to the PDF menu here, PDF documentation. It explains you in detail what regression analysis does in Stata. This is kind of like a quick reference. This is the detailed explanation. It's a very comprehensive documentation. And but now we just want to know what other statistics beyond the estimates the regression command returns. And we can scroll down here and regress stores following in E. And this is the PDF documentation. So it's just like tens and tens of pages of regression analysis and examples. It's worth reading, but I'm not going to read it in this screencast. All right, so we want to do a table, and we do statistics. Then we do post estimation, table of estimation results, and then other statistics displayed in E. So we need to figure out what those other statistics are. I'm going to make this data window a bit smaller so we can see the documentation. And here, then other statistics, we can see that N is the number of observations, sounds useful. Then we have R square, sounds useful. R square adjusted sounds also useful. And then there are other statistics, but these are the ones that you would normally report. Maybe also F statistic, because that's the test statistic. And sometimes you might have a P statistic for the F statistic. So that shows the estimates side by side. And we can see that N drops by 1 because we dropped one outlier. R square goes up, so the model with the log transfer dependent variable fits substantially better. So that is evidence for nonlinearity having been an issue. And then if we do our residual versus beta plot again, here we have plot, we can see that it looks pretty good. So there's no evidence of nonlinearity or heteroscedasticity. If you want to then analyze this data further, you can, for example, turn on the robust standard errors, but I don't see any need for it with these data. The next thing that we need to do is to be able to visualize the results. But before I go there, I'll show you another way of doing the table. So this is like a quick and dirty table that is printed to the console, but you might also want to produce a table that you can put in your article. So we need to have a table that we can embed in a Word document. We can use Stata's customizable tables and collections framework for that. So the collections is kind of like a general framework for constructing tables. So you can collect all kinds of statistics during analysis, and then you lay them out in a table. Then you style the table with a different command, and then that produces you very nice tables that you can then export in various different formats. Let's take a look at tables, and we have customized table of estimation results. This is the better looking table. We do launch and then M1, M2. And the default settings work pretty well, so we can just try. And one of the problems here is that the dependent variable is different, so we need to adjust the settings for this table. We do again statistics, post estimation, and then launch. We recode equations because these are considered different equations because they have different dependent variables. So we create, so we have old equation name ln income is going to be income, like so. So ln income matches income, and then we submit, and that produces as a nice table. So as you can see, this requires a bit more work. And you can customize it this in many different ways. You can, for example, put a different model, or you can put correlations here to the side, or you can add whatever statistics. So this is a very flexible system. If we want to export this, we can do statistics. I had to look at the documentation because I did not remember where the collect export command is located. So we go to data, and then, sorry, statistics, summary tables, and related, and then there's summary and description. There is table of tables and collection, build and style table. So this is a table builder, and you can build all kinds of tables here. So we can actually, I'm not going to go through how this works, but it's very flexible, and we can add more stuff to the table. But we have a table here. We can just export it, and we're going to save it as docs and then export it. It goes to desktop because that is our working directory. So we're going to just call it test table, and okay. And then we can click on it, and it'll open in Word. So this is the way that you can get tables to a Word document, and this is how I export every table that I ever do with Stata if it needs to be in a paper. So that is the second way of making tables. For this assignment, doing this quick and dirty table is okay, but if you want to be more fancy, you can do this table here, and then this is exportable to Word. This one can't be exported, it's just for printing in the Stata console. All right, then we need to be able to visualize the results. So we have two regression models, and let's restore the model one and visualize it. So we can do estimates, restore. You can also do this from the post estimation menu, and then we do graphics, statistics, post estimation, and then we have marginal effects estimated means interactions. So these are basically all very similar commands, or these all run the same command, but they provide you different options for different use cases. And I'm more used to this custom and high dimensional analysis. This is provides you the most options. So I'll just run that. So we want to have a factor to compute the margins over 4. We don't need that. So that is if we want to calculate things or plots over different groups. So our objective here is to calculate a plot where we have the regression line. And we can do at. So we're going to calculate, for example, at different levels of income, education. And then we have at specified specification we create, and we pick fixed value covariate. So we pick education, and that gets from 6 to 16 with increments of 1 year. So 16 is about maximum, 6 is about minimum, and then we click OK. And that plots as the regression line. So what does the line actually look like? We click on OK, then we can plot it, and there's profile plots after marginal analysis. So we just run the plot, and there are all kinds of options. We just do the default. So this shows us the regression line. And to make this regression line a bit better, to show like how well does this regression line explain the data, what we can do is to underlie the actual observations here. So we can actually show the data underneath this regression line. And how you would do it is that you do profile plot, and then there's add plot. We add plot below, we create a plot, and then this plot is scatter. The y variable is income, the x variable is education, and then we accept. And now we have the regression line that explains the data. And we can see here that the first model, the linear model, the line doesn't explain the data well because these data clearly curve up, but the line is straight, so that doesn't really work. We can visualize the second model, which has the log transfer dependent variable. We will first estimate restore the second model. So we're going to estimate restore M2, and now we're going to do statistics post estimation, and marginal effects estimated means custom and high dimensional lawns. And we're going to specify it as before. So this is the same as before, yes. And now we need to specify an expression. So we can specify a prediction, we can create, or specify an expression. So we can do here x predict, like so. The idea here is that we exponentiate the predictions, because if we log transform the dependent variable, then the inverse function of log is the exponential. If we don't do that, then we get the regression analysis on the original, on the log scale. So we're just gonna do default, click OK, and then we can do margins plot. This is not very useful, so because this is now log of salary, log of income. It doesn't make any sense to take a look at the log of income. And what we need to do instead is to do statistics post estimation, and then we're going to predict the exponentiated predictions, and then we click OK, and then we do our profile plots after marginal analysis. And it's still flat because we control for prestige, and this was non-significant, but we can, for example, go for percentage woman, and that gives us a more useful plot. So we do statistics post estimation, then custom and high dimension analysis. Let's rather have at. So we edit, and instead of education, we go from prestige, which is from 20 with increments of, let's say, 10 to 80. So this is the range of the variable that we get from the summary command. And we click OK, and then we do a margins plot. When we change the dependent variable, then we need to change also what we plot. So we edit the plot, and instead of plotting income, education, we plot prestige. And now you can see that this line actually fits the data pretty well. So there's still some occupations, like this is general managers, that are more prestigious than what the model have more income than what the model predicts. But you can see here that the curve actually fits the data pretty well. Now, when you do these plots, you need to pick which variables to plot. And I would pick the ones that are statistically significant over those that are not, because if there's no significant results, then we can't conclude that there is an effect. And typically, if we can't conclude that there's an effect, then the estimated effect is very small and the line is pretty flat. So I would perhaps go with this prestige plot, and then I would go with percentage woman plot and just show and then make a call if it's going from the least prestigious occupation that makes about 3,000 to the most prestigious ones that are expected to make about close to 15,000, holding education constant and holding share of women constant, then that's a pretty big effect. So you can interpret these extremes, or you can directly interpret the regression coefficients that give you the relative effects. So that is the mechanics of how you use data to produce regression results, the various diagnostics plots, two ways of tabulating, and then how you visualize linear and exponential relationships using the margins. The next thing that we need to do is to make a do file that we submit as a part of an assignment, and also that we convert into a report. And how that works is that we open the do file editor, and I'm going to put these windows side by side. And now when you start documenting your analysis, if you do this kind of ad hoc analysis that I just did, then the documentation task is something you do after. But in reality, how researchers tend to work is that you build the do file all the time and you just run it from here. And we start by taking all the commands here. So we're going to copy and paste here. So that is our log. And if we run this, we will get all the results that we got this far. That will produce an error. So we're going to eliminate everything that we don't need and write some comments. And that's what I'm going to do next. So I'm going to load the data. And 2 slashes is a comment. And then these options, you would set them once, so there is no need to set them again. And then we do univariate distributions. Bivariate. These commands don't change how Stata works. They're just there for you to understand what is going on. And they're also there for someone else to understand what your Stata code does or what your analysis does. Documenting your analysis well is super important. It is super important for 3 reasons. And one is that you are not documenting it also for others, but also for future you. So oftentimes, like there's an analysis that you do, and then there might be some time that you don't work on it. And it might be like you work on it a year later when the paper comes back from a review process. And then the reviewers want to see some changes in the analysis. Then if you have this kind of like completely undocumented analysis, it's very difficult to remember what you did and why. The second is that if there is more than one person working with the data, understanding what the other person is doing is a good idea. The third one is that documenting your code helps you avoid errors. So how I actually specify an analysis myself is that I typically write the comments first. So I plan the analysis in the comments, and then I just write the Stata commands under the comments. So that I think about the logic of the analysis first and the mechanics later. If you think about the logic and the mechanics at the same time by just typing Stata commands here, then it's more error prone than thinking about the logic first by writing the comments, documenting what you plan to do, and then thinking about the mechanics. Okay, then we have first regression. And diagnostics. then here we would need to have a really good explanation of why we think ministers are outliers. Because you need to document these kind of decisions, but I will just save time and not write it here while I'm doing the screencast. And so let's see. That's the second regression. We store it and then tabulate. And then we can do, we will just use the second table, and then we can use that table if we want. And we're not going to export it. Then we do graphics, estimate, store, margins, plot. We're going to add the data underneath the plot, because that is something that you should do. And we're going to plot just the prestige. So if you visualize the regression models, it would make more sense to visualize the same independent variable in both. But this is just to show you how the mechanics work. Also, if you want to do diagnostics, then a good way to do the diagnostics is just to copy all this stuff here under regression. So you don't need to click on the commands again. You can just copy paste the commands here in the do file editor. All right, so let's say that this is our assignment 1. This is, of course, not a full assignment, but all these commands that I just demonstrated should be enough for you to complete the assignment. And we're going to call it assignment 1. And then we need to make a report out of it. And this is the kind of the hard part, in that if you're using an old version of Stata, or if you have a very exotic installation of Stata, for example, if your profile is solely on network drive, then this can cause some problems. So let's do producing the report, and we're going to install this package here. I have it already installed, but I'm going to redo it just that you show it. So I'm going to copy paste this, and this is something. It's a Stata package written by this guy called Hakish, and it allows us to make various reports from Stata documents, the Stata do files. So what we need to add is to add it's installing here in the background. And what we need to add here is start a log, and we're just gonna call it assignment 1, and then replace is important, because otherwise the log, if it's open already, if the log already exists, then this will cause a failure. And another thing that I sometimes do is that I do capture log close, and what this does is that it forces any existing logs to close. So if you have a log open, then if you try to open another log, it causes an error. So before we open a log, we need to close an existing log. But if you don't have a log open, then closing a log will cause an error. So this capture command here before log close will cause Stata to ignore any errors that this might cause. So what this does is that it starts a new log, or it closes an existing log if it exists, and starts a new one. And then we close the log at the end, and then finally, after each command, we need to do this img. So each figure. So let's see. These are images, and this is just a kind of like a clunkiness that is a part of the command. These are all figures or graphics. this is a graphic and this is a graphic. And then we do, this is the final lines, and now we run this and it just works. It produces a Word document for us. Before you start adding the log and img, it's a good idea to check that your Stata code runs and produces the result that you want it to do. But I just did it in one go because, there shouldn't be any errors, but there's an error because I forgot to change the log name here. So it's gonna be assignment 1 instead of report. And I'm just gonna rerun that line like so. And then it gives us a Word document, and we can go here. And this Word document contains a log of everything that we just did. And then there's all the figures here. And how we would start writing a report for the assignment, the final report, we would add some text here. So we would have a style heading. So assignment 1 regression, let's call it that. Then description, the assignment, and so on. And then you can add line spacing, change it to make it look a bit nicer and so on. Then we would, for example, here, when we have the describe, we would have, let's do here, clear formatting, explain these results here. So you would basically just explain what the results are. And then you interpret everything, explain your logic by writing comments in the Word file. You submit the Word file, you submit the do file, and then you're done with the assignment.